Section 7.3, Estimating a Population Mean, Sigma Known. Now we move on to finding a confidence interval or a population mean when the standard deviation is known. If the standard deviation is not known, which is often the case, we use a different approach as outlined in the next section. Now, just as we saw that p hat is the best point estimator for the population proportion p, in a similar manner, x bar is the best point estimator for the population mean mu. Our formulas are given below. Now notice these are very similar to the formulas we saw for finding the confidence interval for a population proportion. Again, the confidence interval will take the estimate of the mean, which is x bar, and subtract off the margin of error, or take the mean and the sample mean, x bar, and add on the margin of error. The way we find the margin of error, we still have to find the z alpha over 2, z sub alpha over 2 like we did before. This time we're going to multiply by sigma divided by the square root of n. So very similar to what we did for population proportion, but the formulas are slightly different. Well, again, we have some requirements that must be met. Has to be from a simple random sample. The population standard deviation must be known, and the population either has to be normally distributed, or if not, the sample size has to be greater than 30. Besides all that, the steps to finding the confidence interval are very similar to what we did before. So let's just jump into an example. Example 1. Total plasma volume is important in determining the required plasma component in blood replacement therapy for a person undergoing surgery. Plasma volume is influenced by the overall health and physical activity of an individual. And the reference for this comes from the Manual of Laboratory and Diagnostic Tests by F. Fischbach. Suppose that a random sample of 45 male firefighters is tested, and they have a plasma volume sample mean of 37.5 milliliters per kilogram. Assume that sigma is equal to 7.5 milliliters per kilogram for the distribution of blood plasma. Find a 99% confidence interval for the population mean blood plasma volume in male firefighters. Interpret your results. Well, again, I like to write down the information that we already know. We do have a sample mean, which is 37.5. And we also know the standard deviation sigma, which they told us was 7.5. First, we want to worry about alpha. Well, alpha, remember, is 1 minus the confidence level, which is 99%, so 1.99, and we found this value before already, but just how we find it, we take that, we divide by 2, so that gives us 0.005. So z sub 0.005 we found before to be 2.575. And the way we get that is we look on our table. Here's 0.051 and 0.049. The z-score that goes with that is 2.57 or 2.58. And last time we just went ahead and split the difference and said 2.575 since neither one is exactly on 0.005. Okay, now that we have that, we go to calculating the margin of error. So E is equal to z sub alpha over 2 times sigma over the square root of n, just as it was stated here in our formula. Well, we know our z-score, that's 2.575. Sigma, we were told, is 7.5, and the sample size, which we did not write down, we should have, which is 45, so square root of 45 down here. Let's see what we get. And I'm getting 34.6211 and 40.3789. So our confidence interval is from 34.62 up to 40.38. And the way we would interpret that, remember we said to be careful about how you interpret that. We could say we are 99% confident that the interval from 34.62, and we should put our units on that, truly. So we are 99% confident that the interval from 34.62 milliliters per kilogram to 40.38 milliliters per kilogram contains the true mean of the average for the firefighters. Remember, we don't want to say that we're 99% confident that the mean falls in that interval. It's that the mean contains the interval, so be careful with that. Okay, and similar to before, when we know the confidence interval we want to obtain, but we do not know the sample size, we use the following formula. So in our sample size, we take our z sub alpha over 2 times sigma divided by e, and we're going to square all of it. So we'll try an example doing that. Example 2. A wildlife study is designed to find the mean weight of salmon caught by an Alaskan fishing company. A preliminary study of a random sample of 50 salmon showed the standard deviation to be approximately 2.15 pounds. How large a sample should be taken to be 99% confident that the sample mean x bar is within 0.2 pound of a true mean weight mu? So let's see what we do know. We know that the standard deviation is 2.15, and we know that E is 0.2, because if we want to be within 0.2, that means either higher or lower, but within 0.2 pound of the true mean weight mu. So here's our formula. N equals z sub alpha over 2 sigma divided by E, and all of that will be squared. So we need that z sub alpha over 2, and we've been doing 99% a lot. Just keep in mind that sometimes it could be 95, it could be 90, it could even be as low as 80, and you want to understand how to find that z-score. After a while, maybe some of the same few z-scores will pop up and you'll get to know them, but just make sure you understand that you're doing the 1 minus 0.99 to get the alpha, dividing that by 2, and then looking up the score on your table. But we've done 99% quite a bit, so we know that this z sub alpha is 2.575, sigma is 2.15, divided by E 0.2, and all of that will get squared. And I get a value of 766.25, and if we round to the nearest whole number, 766. So to be 99% confident that we will be within 0.2 pound of a true mean weight mu, we need a sample size that's 766 salmon large.